Chapter 7 is sampling distributions. Now, sampling distributions is probably the most, if not one of the most fundamental and crucial concept in statistics. All other statistical analysis of any kind rests on the concepts discussed in chapter 7, the sampling distribution. If sampling distribution doesn't work, nothing else in statistics will work. So this is a very crucial topic, and it is extremely essential, necessary to have a good understanding of what sampling distribution is. So for this chapter, we need the PowerPoint file, and we need the formulas file that needs to be printed out, and of course you need to download the Excel shell file and work all the problems that I work on Excel. You need to work those problems in the Excel file that you have downloaded as well. Okay. Now in this chapter we're going to learn about two basic concepts. One is what is sampling distribution, and then the importance of central limit theorem that plays on the sampling distribution. Two things: sampling distribution, central limit theorem. So these are the two fundamental concepts covered in this chapter. Okay. So what is a sampling distribution? Sampling distribution is a distribution associated with the sample statistic. Okay. First, let's get some theoretical framework done, the fundamental theoretical understanding. And then we will look at concrete examples of that theoretical concept. Now suppose we have a population. Okay. Now we take a random sample from this population. So sample 1. And we compute the average of that sample. So we'll call that x bar sub 1. And normally we take only one random sample and that's it, and we will do the statistical analysis. But for the purpose of understanding sampling distribution, let's assume that we take another sample of the same size, sample 2, and compute the average for that sample. Okay. Then we keep doing that as many times as possible. Okay. Now this could be infinitely many times, but for the sake of understanding sampling distribution, let's say that we have done that, and now we have a collection of all of these different samples, sample averages. So that is another population. So here are just x values. Now we take random samples, all possible random samples of size n. So let's say size is n. Sample size is n. So now we have a second population, and this is a population of samples or sample means. So the probability distribution of this population, the population of sample means, is called sampling distribution. So sampling distribution is nothing but a secondary population derived from the primary one. So we normally will take only one sample, and based on the sample average and standard deviation, we will make statistical inferences and estimation. But for the purpose of understanding sampling distribution, we are considering, we are doing a mental exercise. Okay, so we take all possible samples and we have a bunch of collection of x bars, and this is called the sampling distribution. Now let's try to understand what this probability distribution will be like. Okay, so we have the primary population, and let's assume that the primary population has parameters mu and sigma, for mean and standard deviation. And then we have the sampling distribution of sample mean with sample size equal to n. So that is the second population. Now, to understand this sampling distribution, we want to know what this mu of x bar will be. So this is the primary population with mean, mu and sigma. So what will be the mean of this population? What will be the standard deviation of this population? Okay. And what will be the probability distribution of this population also? Okay, we would like to know that. Now it turns out that no matter what this primary population may be, mu sub x bar will always be equal to mu itself. The mean here will be the same mean as that one. And further, sigma sub x bar will be sigma over square root of n. So this population will have lot smaller standard deviation, and this is called standard error, by the way. To differentiate between the standard deviation here and the standard deviation here, we use the terminology standard error for the sampling distribution. All right. Now, what about the probability distribution of this secondary sampling distribution? To determine the probability distribution of the sampling distribution, we have what is called central limit theorem. The central limit theorem is the cornerstone of everything that we do in statistics. And what does it say? Okay. It says if the primary population is normally distributed, is normal, so with mean equal to mu, standard deviation sigma. Okay. If this is normal, then the sampling distribution will be normal as well. With mean of x bar equal to mu and sigma sub x bar equal to sigma sub square root of n. Okay, so this is the first part of the central limit theorem, okay, which is good, but the power of central limit theorem comes from the second part of this theorem, and that is if the probability distribution of the primary population is not normal or unknown, either case. Okay. We don't know what the population probability distribution is for the primary population. Then what? Then the central limit theorem says then the probability distribution for the sample means, that's this secondary population, the population means, will be approximately normal. Okay, so this is where the power of central limit theorem comes from. Okay, it will be approximately normal, but how approximate is this? This is kind of vague, but the the additional statement that comes with this, that's what gives the oomph for this theorem. Okay, as sample size n increases, the distribution for x bar will become more and more closer to normal. Of course, with mean is mu itself, and sigma sub x bar is sigma over square root of n. That part is the same for both parts. So in central limit theorem, we have two parts. One is if we know that the population we begin with is normal, then it doesn't matter. The secondary population of x bars will be normal no matter what, whether its sample size is 2 or 25 or 2500, doesn't matter. Sample size doesn't matter. But if the original population is not normal, or you don't know what it is, in most cases that would be the case. You may not know what the population probability distribution is for the population. Then the population distribution for x bar will be approximately normal, and as sample size increases, it will become more and more closer to normal distribution. And that's why if we take a larger sample, we can always assume that the x bar will follow normal distribution. The normal cutoff point that we use is if n is greater than or equal to 30. Okay, n greater than or equal to 30 is the kind of thumb rule that we use for large sample. Okay. Now, if the population has a symmetric distribution, not normal but kind of normal, then even for smaller, like n greater than or equal to 15 would be sufficient for us to use normal distribution for x bar. So this is the reason why, that is, no matter what the original population is, when we compute x bar, then we can start using normal distribution for x bar irrespective of what the original population distribution was, as long as n is greater than or equal to 30, which is really a thumb rule. Okay, for uniform distribution, for example, suppose you have a population is uniform, population distribution is uniform. Then uniform is kind of a symmetric distribution, so even for very small sample sizes, as small as 15, x bar would exhibit overwhelmingly normal distribution. So that is where the power of central limit theorem comes from. So central limit theorem is what gives us the authority to use normal distribution for sample mean, irrespective of the original population. So with this theoretical background, let's look at the rest of the PowerPoint file.